Welcome students. In this session, we will discuss rings of endomorphisms and quaternions. An endomorphism of an abelian group A is a homomorphism from A into itself. In this session, we will establish that the set of endomorphism of an abelian group forms a ring. We also discussed that the quaternions forms a skew field under addition and multiplication. Also, the statement of Wedderburn's theorem is discussed. Definitions. Let G and H be groups. A mapping phi from G to H is called a homomorphism if phi of x into y equal to phi of x into phi of y for x y belongs to G. If phi is 1 to 1, that is injective, then it is an isomorphism or monomorphism of G into H. If phi is onto, that is surjective, then it is an epimorphism of G onto H. If phi is both 1 to 1 and onto, that is bijective, then it is called isomorphism of G onto H. In that we say that G is isomorphic to H and is denoted by G isomorphic to H. A homomorphism of an abelian group G into itself is called an endomorphism of G. An endomorphism of G that is both 1 to 1 and onto is called an automorphism of G. Rings of endomorphisms. Let A be an additive abelian group. We denote the set of all endomorphisms of A by hom A or by end A. For phi and psi belongs to hom A, the homomorphism addition phi plus psi is defined in terms of its values on each A belongs to A. That is by phi plus psi of A is equal to phi of A plus psi of A, and the homomorphism multiplication, that is function composition, is defined by phi psi of A is equal to phi of psi of A. We now establish that set of endomorphisms of an abelian group forms a ring. Theorem 1. Let A be an additive abelian group. The set hom A of all endomorphisms of A forms a ring under homomorphism addition and homomorphism multiplication. Proof. We first show that hom A is an abelian group under homomorphism addition. First of all, we show that phi plus psi is a homomorphism. Phi plus psi of A plus B equal to phi of A plus B plus psi of A plus B by the definition of homomorphism addition, which is equal to phi of A plus phi of B plus psi of A plus psi of B, since phi and psi are homomorphisms, which is equal to phi of A plus psi of A plus phi of B plus psi of B, since A is an abelian group, which is equal to phi plus psi of A plus phi plus psi of B, again by the definition of homomorphism addition. Hence, phi plus psi is a group homomorphism from A to A, and hence phi plus psi belongs to hom A. Thus, closure property of the operation homomorphism addition in the set hom A is verified. 2. Phi plus psi of A is equal to phi of A plus psi of A, which is equal to phi of A plus psi of A by the commutativity in A, which is equal to phi plus psi of A. Hence, phi plus psi equal to psi plus phi, and the addition in hom A is commutative. 3. For phi psi theta belongs to hom A, we have phi plus psi plus theta of A is equal to phi of A plus psi plus theta of A, which is equal to phi of A plus psi of A plus theta of A, which is equal to phi of A plus psi of A plus theta of A by the associativity of addition in group A, which is equal to phi plus psi of A plus theta of A, which is equal to phi plus psi plus theta of A. If E is the identity of A, then the homomorphism 0 defined by 0 of A is equal to E for A belongs to A is an additive identity in hom A. This can be seen as follows. For phi belongs to hom A and A belongs to A, we have phi plus 0 of A is equal to phi of A plus 0 of A, which is equal to phi of A plus E, which is equal to phi of A. Since phi belongs to hom A and A belongs to A are arbitrary elements, then the above shows that phi belongs to hom A and A belongs to A. We have phi plus 0 is equal to phi for phi belongs to hom A. 5. For phi belongs to hom A, minus phi defined by minus phi of A is equal to minus of phi of A is in hom A, since minus phi of A plus B is equal to minus phi of A plus B, which is equal to minus of phi of A plus phi of B, which is equal to minus phi of A minus phi of B, which is equal to minus phi of A plus minus phi of B, and phi plus minus phi equal to 0. Thus, minus phi is the additive inverse of phi in hom A. Combining the above, we have hom A under addition is an abelian group. The verification that hom A is closed under homomorphism multiplication is left as an assignment. We now verify that the distributive laws of homomorphism addition and homomorphism multiplication hold in hom A. Theta into phi plus psi of A is equal to theta into phi plus psi of A, which is equal to theta into phi of A plus psi of A, which is equal to theta of phi of A plus theta of psi of A, since theta is a group homomorphism, which is equal to theta phi of A plus theta psi of A by the definition of homomorphism multiplication. Thus, theta phi plus psi is equal to theta phi plus theta psi. Also, the right distributive law follows from the following: psi plus theta phi of A is equal to psi plus theta of phi of A, which is equal to psi of phi of A plus theta of phi of A, which is equal to psi phi of A plus theta phi of A, which is equal to psi phi plus theta phi of A. This completes the proof of the theorem. The following example illustrates that the above ring Hom A need not be commutative. Example 1. Consider the abelian group set cross set under addition. We can specify an endomorphism of this group by giving its values on the generators 1 0 and 0 1 of the group set cross set under addition. Define phi belongs to Hom set cross set under addition by phi of 1 0 is equal to 1 0 and phi of 0 1 is equal to 1 0. Define psi belongs to homomorphism of set cross set under addition by psi of 1 0 is equal to 0 0 and psi of 0 1 is equal to 0 1. Note that phi maps everything onto the first factor of set cross set and psi collapses the first factor. Thus, psi phi of n m is equal to psi of phi of n m, which is equal to psi of n plus m 0, which is equal to 0 0, while phi psi of n m is equal to phi of psi of n m, which is equal to phi of 0 m, which is equal to m 0. Hence, phi psi not equal to psi phi. Example 2. Let f be a field and let f of x under addition be the additive abelian group of the ring f x under addition, the ring of polynomials with the coefficients in f. In this example, to simplify the notation, we denote the additive group by f of x. We consider Hom f of x. One element of Hom f of x acts on each polynomial in f x by multiplying it by x. Let this endomorphism be x. So, x of a naught plus a 1 into x plus a 2 into x square plus etcetera a n into x raised to n equal to a naught into x plus a 1 into x square plus a 2 into x plus etcetera a n into x raised to n plus 1. Verifying that x is an endomorphism is left as an assignment. Another element of Hom f x is formal differentiation with respect to x. The familiar formula, the derivative of a sum is the sum of derivatives, guarantees the differentiation is an endomorphism of f x. Let y be this endomorphism. So, y of a naught plus a 1 x plus a 2 x square plus etcetera a n into x raised to n equal to a 1 plus 2 a 2 x plus etcetera n a n x raised to n minus 1. It can be seen that y x minus x y equal to I, the unity in Hom f x, so that x y not equal to y x, where x and y is above. Multiplication of polynomials in f x by any element in f also gives an element of Hom f x. Theorem 1. If G is equal to set of all G I belongs to I is any multiplicative group and R be any commutative ring with unity, and R G is equal to sigma I belongs to I, A I G I, A I belongs to R, G I belongs to G, where all but a finite number of A I are 0, then set of all R G under addition multiplication is a ring. Proof. 1. We define the sum of two elements in R of G by sigma I belongs to I A I G I plus sigma I belongs to I B I G I equal to sigma I belongs to I A I plus B I into G I. Observe that A I plus B I equal to 0 except for a finite number of indices I. So, sigma I belongs to I A I plus B I into G I is an element of R of G. It can be easily verified that R of G under addition is an abelian group with additive identity sigma I belongs to I 0 into G I. 2. Multiplication of two elements of R of G is defined by the use of the multiplication in G and R and is as follows: sigma I belongs to I A I into G I into sigma I belongs to I B I into G I equal to sigma I belongs to I sigma G j G k is equal to G I A j B k into G I. Again, at most a finite number of sigma G j G k is equal to G I A j B k are non-zero. Thus, multiplication is closed in R of G. 3. The distributive laws follows at once from the definition of addition and the formal way we used distributively to define multiplication. For the associativity of multiplication, sigma I belongs to I A I into G I into sigma I belongs to I B I into G I into sigma I belongs to I C I into G I, which is equal to sigma I belongs to I A I into G I into sigma I belongs to I sigma G j into G k equal to G I B j C k into G I, which is equal to sigma I belongs to I sigma G h into G j into G k equal to G I A h into B j into C k into G I, which is equal to sigma I belongs to I sigma G h into G j equal to G I A h B j into G I into sigma I belongs to I C I into G I. which is equal to sigma I belongs to a ai into gi into sigma I belongs to a bi into gi whole into sigma I belongs to a ci into gi. This completes the proof of the theorem. Definition: group ring. The ring defined above is the group ring of G over R. Definition: group algebra. If F is a field, then f of G is the group algebra of G over F. Example 3. The group G is equal to set of E A is cyclic of order 2 with the generator A. Since set 2 is equal to set 0 1 is a field, set 2 of G is the group algebra and is given by set 2 G is equal to set of all 0 into A plus 0 into A, 0 into E plus 1 into A, 1 into E plus 0 into A, 1 into E plus 1 into A. If we denote the elements in set 2 G in the obvious natural way by 0, A, E, E plus A, the addition and multiplication tables are given below. Consider addition. Take first row 0 plus 0 equal to 0, 0 plus A equal to A, 0 plus E equal to E, 0 plus E plus A is equal to E plus A. Second row A plus 0 equal to A plus A equal to 0, A plus E equal to E plus A plus E plus A equal to E. Third row E plus 0 equal to E, E plus A equal to E plus A, E plus E is equal to 0, E plus A is equal to A. Fourth row E plus A plus 0 is equal to E plus A, E plus A plus A is equal to E, E plus A plus E is equal to A, E plus A plus E plus A equal to 0. Consider multiplication. First row 0 into 0 equal to 0, 0 into A equal to 0, 0 into E equal to 0, 0 into E plus A equal to 0. A into 0 equal to 0, A into A equal to E, A into E equal to A into E plus A is equal to E plus A. Third row E into 0 equal to 0, E into A equal to A, E into E equal to E, E into E plus A is equal to E plus A. Fourth row E plus A into 0 equal to 0, E plus A into A is equal to E plus A, E plus A into A, E is equal to E plus A, E plus A into E plus A equal to 0. In the above, note that E plus A into E plus A equal to 1 into E plus 1 into A into 1 into E plus 1 into A, which is equal to 1 plus 1 into E plus 1 plus 1 into A, which is equal to 0 into E plus 0 into A. Example of a skew field, the quaternions of Hamilton. Definition: skew field. A non-commutative division ring is a skew field. We consider R the field of real numbers under addition. We take Q is equal to R cross R cross R cross R, the direct product of R. We define addition on Q by addition by components. It can be verified that Q under this addition by components is an abelian group. Let us rename certain elements of Q. We shall let 1 is equal to 1 0 0 0, I is equal to 0 1 0 0, j is equal to 0 0 1 0 and k is equal to 0 0 0 1. We furthermore agree to let A1 is equal to A1 0 0 0, A2 I is equal to 0 A2 0 0, A3 j is equal to 0 0 A3 0 and A4 k is equal to 0 0 0 A4. In view of our definition of addition, we then have A1 A2 A3 A4 is equal to A1 plus A2 I plus A3 j plus A4 k. Thus, A1 plus A2 I plus A3 j plus A4 k plus B1 plus B2 I plus B3 j plus B4 k is equal to A1 plus B1 plus A2 plus B2 into I plus A3 plus B3 into j plus A4 plus B4 into k. To define multiplication on Q, we start by defining 1 into A is equal to A into 1 is equal to A for A belongs to Q. To define multiplication on Q, we start by defining I square equal to j square equal to k square equal to minus 1 and I into j equal to k, j into k is equal to I, k into I is equal to j, j into I is equal to minus k, k into j is equal to minus I and I into k is equal to minus j. Note the similarity with the so called cross product of vectors. These formulas are easy to remember if we think of the cyclic sequence I j k I j k. We define a product to be what it must be to make the distributive laws hold, namely A1 plus A2 I plus A3 j plus A4 k into B1 plus B2 I plus B3 j plus B4 k, which is equal to A1 B1 minus A2 B2 minus A3 B3 minus A4 into B4 plus A1 into B2 plus A2 into B1 plus A3 into B4 minus A4 into B3 I plus A1 B3 minus A2 B4 plus A3 B1 plus A4 B2 j plus A1 B4 plus A2 B3 minus A3 B2 plus A4 B1 k. Theorem 2. The quaternions Q form a skew field under addition and multiplication. Proof. The proof includes the discussion just above and the following. Since I into j equal to k and j into I is equal to minus k, we see that I into j not equal to j into I. Hence, multiplication is not commutative. So, Q is definitely not a field. The only axiom that we prove is the existence of a multiplicative inverse for a 1 plus a 2 I plus a 3 j plus a 4 k with not all a I equal to 0. Computation shows that a 1 plus a 2 I plus a 3 j plus a 4 k into a 1 minus a 2 I minus a 3 j minus a 4 k equal to a 1 square plus a 2 square plus a 3 square plus a 4 square. If we let mod a is equal to a 1 square plus a 2 square plus a 3 square plus a 4 square and a bar is equal to a 1 minus a 2 I minus a 3 j minus a 4 k, we see that a bar by mod a square is equal to a 1 by mod a square minus a 2 by mod a square I minus a 3 by mod a square j minus a 4 by mod a square k is a multiplicative inverse for A. The verification of other axioms are left as an assignment. We conclude this session by stating the famous Wedderburn's theorem. Theorem 3, Wedderburn's theorem. A finite division ring is a field. Remark: in view of Wedderburn's theorem, we conclude that there are no finite skew fields. Now, it is time to summarize the session. In this session, we have seen that the set of endomorphisms of an abelian group forms a ring. We have described that the quaternions form a skew field under addition and multiplication. Also, the statement of Wedderburn's theorem have been discussed. Before we attend the next unit, please try to answer the following questions. Find an example to show that if a finite multiplication subgroup of a strictly skew field need not be cyclic. Show that the ring N of set 2 cross set 2 under addition is not isomorphic to the ring set 2 cross set 2 under addition multiplication. Prove Wedderburn's theorem. See you next time. Till then, goodbye.